We're now going to talk about properties of logarithms, and the properties of logarithms are something that we'll be using quite frequently here. And so we'll first start off with this change of base, which we had mentioned in the last video. We had mentioned it in relation to the fact that our calculators typically only have two logarithms on this. So this is the change of base formula. So we start off with the log base a of x, and this is what we're trying to compute. Well, the change of base formula states that the log base a of x is equal to the log base b of x over the log base b of a. So we can use any logarithm here, because base b, this is just some other base other than a, and you can use any base here, doesn't matter what b is, as long as b satisfies what we need it to satisfy in order to be a logarithm. But we can then compute what the log base a of x is. This is why some calculators don't have more than just two log functions on there, because we don't really need more than two. And the reason it still has two is because common log is a very common, as the name might imply, logarithm that's used, but natural log is just as common, or in some ways I think sometimes it's used more frequently than the common log is. Alright, so to kind of summarize this also though in terms of the ones that you'll typically see on your calculator, this would be that log base a of x would be the common log of x over the common log of a, or that the log base a of x is equal to the natural log of x over the natural log of a. So let's just do an example here where we already kind of know what the answer is. And what do I mean by that? Well, let's look at the log base 2 of 32. And if we sit here for a second, we can get that this would be 5, because 2 to the 5th power is 32. Now, let's suppose, though, I want to actually compute this using my change of base formula. So I could say that this would be log of 32 over the log of 2. Now, we wouldn't ever really write the decimals out here. You really just do this on your calculator. But just to kind of show you what's going on, if you did the log of 32, you'd have 1.505149 because it goes on forever and it's an irrational number. And then this would be divided by the log of 2, which is 0.301029 and it goes on forever without repeating. Now, as I said, typically you wouldn't ever write these decimal numbers down. You'd just do this computation just directly in your calculator. And if you do that, though, you get that this is 5, which shouldn't be surprising that we do get that, because otherwise the change of base formula wouldn't work properly. Now, you can do it again. It doesn't matter whether you use the common log or the natural log. So this is also equal to the natural log of 32 over the natural log of 2, which if you do that computation, you get 5 as well. Now, the advantage of this is it allows us to compute bases, or not bases, it allows us to compute logarithms when the bases are something that we don't have in our calculator. And as an example here, log base 3 of, let's do 11. Now, I don't know what the log base 3 of 11 is, and I was saying, okay, well, what exponent do I put on 3 in order to get 11? Well, that's not obvious either, because if I do 3 squared, I get 9, and if I do 3 cubed, I get 27. Well, okay, so clearly it's somewhere between 2 and 3, but I have no idea. Now, I could play guess and checking, but that seems like a kind of tedious way, so I'll do my change of base formula. Now, you only have to ever do one of these. You don't have to do both common and natural log. And I tend to always do natural log. I don't know why. I just tend to always do the natural log one. So this would be natural log of 11 over the natural log of 3. So if I look at this here, this would be natural log of 11 divided by the natural log of 3. And we do get 2.18265 going on forever. And if we rounded this, this would be approximately 2.1827. Now again, we can verify this by just looking at what 3 to the 2.1827 is. And this is equal to 11.000503 dot dot dot. And of course it's not exactly 11 because we rounded our answer here, which is what you typically would do, but we can clearly see that this is basically just 11. So that exponent that we got is absolutely correct. Now, this change of base formula is something we can prove, and I may prove it a little bit later on in one of the videos here. But for now, I'd like to move on to some other properties of logarithms, and we will prove some of these here. So, other properties of logarithms. And so we have a product property. And the product property is where if you have the log base A of m times n, this is equal to the log base A of m plus the log base A of n. Now we will prove this here in a second, and we'll also just kind of justify by talking about it why this actually kind of makes sense. Alright, but then we also have, besides product property, we have a quotient property. And the quotient property, of course, is if you have log base A of m over n, and you might guess what this would do. This would be log base A of m minus log base A of n. And then we have one other very important property here, and this is called the power property. And the power property is where you have log base A of m to the little n power. This is equal to n times log base A of capital M. So these are our three very important log properties. And as I said, we're going to go ahead and prove some of these because these aren't just magic formulas. They actually can be proven. So let's go ahead and prove the log base A of m times n is equal to the log base A of m minus the log base A of n. So to prove this, well, we're going to do some kind of just formula manipulation here. So what we're first going to do here is we're just going to say, I'm going to let y equal, actually, I'll do x first. I'm going to say let x equal the log base A of m, and let y equal the log base A of n. So the right-hand side here, actually I said I was proving the product property one. This is a plus right there. So the right-hand side would just be x plus y. But before we get on to that here, we're going to go ahead and convert these to exponential forms. Because remember, the definition of logarithms, we can rewrite these as m is equal to a to the x and n is equal to a to the y. But then what are we wanting to do? Well, we want to see what m times n is. Well, m times n is equal to a to the x times a to the y. But of course we know what we do when we're multiplying and we have the same base. We add those exponents. So a to the x plus y. But now convert back to logarithm. And you have log base a of m times n is equal to x plus y. But then substituting in, you have log base a of m times n is equal to the log base a of m plus the log base a of n. And this really shouldn't be too surprising to us, because I'm going to scroll back up to these properties here. When we first started talking about logarithms, fairly early in the video, what was one of the most important things I said you could know is that logarithms give us exponents. Okay, so if a logarithm gives us exponents, and you're multiplying something together, what do you do to the exponents? Well, if you multiply, what do you do to the exponents? You add exponents. So, if you divide things, what do you do to your exponents? You subtract. And then, if you do a power to a power, what do you do to the exponents? You multiply the exponents. So, the properties, now we could prove the quotient property and the power property. I'm not going to prove those two properties here, but we could go ahead and do that. Now I'm actually going to end the video here. It's a little bit shorter video because I'd like to have the next video be just about example problems using these properties.